Um, I will have your. I've been reading through the homeworks. I just got to put grades on them and then send them back, and then put up your new homework. I should have those done today. I'm a little behind in my assignments, so I'll have your new assignments for the material we went over last week and the material we're still going over this week on WebCT today, and then also have your assignments back. Now, before we go on, I would like to bring up one thing that I think, like looking at the answers, one kind of point of during the introduction and also during some of the multiprocessing that I kind of missed. One thing that I kind of want to emphasize is that actually a lot of what we talk about in operating systems, we do a lot of theoretical computer science type stuff, but another aspect of operating systems is economical, is business. Okay, one of the main reasons for the things that we do in operating systems is to make it so that we don't only gain efficiency in terms of how we utilize processors and disks and resources like that, but it also a big aspect of it is how do we make computing cheaper? Okay, so two of the major kind of questions that came up in the questions I assigned you that kind of touch on this are, one was the idea of time-sharing systems versus kind of personal systems that you kind of have exclusive access to. And the other one was in terms of, for example, cache memory and things like that, and what happens if we could make the cache as big as, the level that it's, the level below it that it's caching for. Okay? Both of those questions are kind of economics questions. Okay, and what I mean by that is this. What is a good reason that we as a user would have for using a time-sharing system? Okay, obviously, a time-sharing system, on one hand, can come up in the context of we have our own machine, and we still call it a time-sharing or multitasking or task-switching system, even though we're the only ones using it. It's just our own tasks that are running on it. But one of the kind of initial purposes of doing time-sharing or multitasking systems was that multiple users will use it, right? So what would the reason be for using a time-sharing system like that if you have the option of not using a time-sharing system? So for example, we in the computer science department, right, we have systems that we have access to, like one, for example, is the one in CS400. There's now called Qubit, which used to be Yamacron. I mean, that's a system that we all share, right? Then there is there's another big system in the computer science department called we have one called Hydra, which is a very big SGI workstation, multiple processors, like 24 processors, I think. We have another one called BMCC, which is a very big multiprocessor Xeon system that we use for a lot of bioinformatics stuff, right? All of these systems that I mentioned, they're powerful systems, but then there's also plenty of powerful personal computer systems that we have as well. So what kind of reason would we have for using one of those multiprocessor systems? For example, one of the clearest examples is BMCC, right? This system is a Linux system running on Intel Xeons that runs in the department, okay? There's plenty of uniprocessor Intel Linux boxes, so there's no difference in operating system. There's no difference in programming environment, things like that. Why would I use BMCC? It's a time-sharing system in the sense that multiple users have to share it. Why would I go to that system instead of using? Save money in what sense, though? Hopefully I save time. Hopefully it's more efficient for me to run there. But how? In what sense is money saved? Right. So I mean, for example, like if I use my personal, let's say I do have a personal machine, right? I have a workstation that's a a Linux box or whatever. And I do have that. And BMCC is there. Okay? So now there's no more additional outlay of cash. Nobody's buying any new systems. Is there still a case where I'd want to use BMCC instead of my machine? There's still a factor here that we need to look at of why we choose BMCC over. BMCC is this, I think it's a 4-processor Xeon Dell Linux box, whereas my workstation in the department is a Pentium 4 probably Dell workstation. Right, it's very powerful, right, compared to my machine. So why would I go to BMCC even though I have to share it? Because even though I'm sharing it, there's a very good possibility that my share is more powerful than my standalone exclusive use machine.
Powerful in which sense?
In any sense, I mean, in whatever sense I need. In other words, in any sense that it is more powerful, that's the only reason I have to go use it. In other words, if the disk isn't as fast as my local workstation, there's no reason for me to go to BMCC if disk is the performance factor I'm looking at.
I mean, one individual, how much they need, which could provide their, but not here. I mean, how much?
In other words, if my personal workstation can provide what I need,
I mean, is it what a person could really interact with the computer?
it's if I can't accomplish it on my local workstation, I need to go to a time-sharing system. I don't know what you're doing. And there's plenty of cases where one job might make sense to run on my local workstation and another job on BMCC. The key is that if I don't get more performance by going to a shared system where I'm sacrificing some performance by sharing, in other words, if the sacrifice of sharing that system with others is greater than the level of performance I get compared to not sharing with others on a different system, I should not go to that other system. In other words, the key thing here is that there's no reason, in other words, the question of when should we go to a time-sharing system as opposed to a personal computer system, only when we get more performance, right? There's no other factors that we've seen. There's no aspect to the design of time-sharing systems that makes them more appealing than a personal computer system, except for the regular benchmarks that we use to measure these different systems. In other words, disk speed, disk space, memory, all the processor speed, processing power in general, maybe the fact that there's multiple processors. Another good reason to go to a time-sharing system is maybe they do regular backups on that, and they don't do regular backups on your local machine, right? But there has to be some economical reason for going to that time-sharing system. Nothing about time-sharing system makes them better than an exclusive use system, except for the fact that the computer science department is willing to buy us a 4-processor Xeon server for the department and not willing to buy us 4-processor Xeon systems for the desktop. If they got a huge budget and said, okay, everybody gets a 4-processor Xeon system to sit at their desk, there's absolutely no reason to go to BMCC, right? So the main thing is that why would you go to a time-shared system? Well, because you can't afford that amount of processing power in a standalone system. Okay, so there were plenty of good answers to that question on the homework, but they all kind of skirted around the issue of the fact that you can't afford it, right? Because the only real reason is that you can get essentially economies of scale by buying for multiple people instead of just buying for one person. But if you can afford that for your person, for your individual workstation, yes, it's better in all ways, right? If given the choice between dividing resources between multiple users and not dividing resources between multiple users, you will get better performance out of not dividing resources. In other words, if you take 2 equal machines and say, do you want to be on the time-sharing one or the exclusive use one? The answer is always the exclusive use one. But the key here is that that question doesn't come up. That's a silly question to ask, right? The real question is, do you want this very powerful time-shared system or this weaker exclusive use system? That's the only question that should come up. Obviously, if you go to the other end and say, I have this more powerful exclusive use system and this less powerful time-shared system, there's, that shouldn't even enter into radar, right? Plus, your department's budget's all screwed up. That's the case as well, right? Because there's no reason to go to a time-shared system if you're not providing more power. And power is the kind of vague term there. Power might be disk, it might be hard drive space, it might be the fact that they back up and you don't. And then also there's some kind of particular ways where power gets very, very kind of vague. For example, if there's a piece of software on one of the systems that you don't have. Obviously, that's a compelling reason that that system is more powerful than yours. It has the software you want to run and yours doesn't. So for example, if you need to write a piece of software on Solaris, it doesn't matter how weak Qubit is, you go to Qubit because it's the only one. It's obviously the most powerful system running Solaris that you have, right? Because you don't have Solaris on your box. Okay, so that's one thing. The other one kind of came into play with talking about cache, right? One of the questions was if, let's say I'm looking at my main memory, I have a gig of main memory, and then I have a meg of cache. Okay, if I could make cache a gig, why not do that?
Yeah, that question, also, I think it's not tricky, at the same time it's kind of, I felt like tricky. Because if cache is hard drive, then what is hard drive? Hard drive is cache, then what is?
Well, hard drive adds an additional twist, and we'll talk about that in a second, but let's stick to the example I gave. There's a gig of memory, of main memory, of RAM, and then there's a meg of cache. Okay, I say, well, here's a system where I have a gig of cache memory, and I basically just throw away main memory. Which system's better? The one that has the 1 meg cache and a gig of main memory, or the one that has a gig of cache? Absolutely not. It's going to be far superior. There's no way that the other system could even, there's no way the other system could be better.
Because the reason I said ultimately it has to find the program or the bytes, because when you have cache is a gig, 1 gig, you get all the space filled out with the memories in hard drive, right?
Hard drive. The thing is if you can load from hard drive into RAM, why can't you load from hard drive into cache? In fact, the mechanisms that go from memory to cache are complex. In other words, all the things that we talked about, like briefly about cache and things, all those things could be eliminated. All this first in, this most recently used and all that stuff, all of that could be eliminated and we could just load directly into cache from disk. The same program that we loaded into memory from disk, we can now load into cache from disk. In other words, skip the middleman, go directly up. The thing is it's like memory, just faster. There's no downside. Okay? Looking at it like that. But obviously, we don't do that, right? So there's got to be some hidden downside. What's our hidden downside? You can't afford it. Okay? A gig of cache is astronomically expensive. Okay? A meg of cache that we have these days is, it's still amazing that we have caches that big. Caches used to be 2K, 1K. Now they're a meg and greater. Okay? That's already amazing. Having a gig of that, absolutely not. We can't afford it. Okay? The idea is that cache is a game of economics. Okay? It's saying, I want to give you the performance of this prohibitively expensive this prohibitively expensive fast memory. I want to give you that performance, but for the price of the slower big memory. Okay? If you can make your prohibitively expensive memory as big as the other memory, it's better. Okay? But the only time that really makes sense is if the price of cache and the price of main memory are equal. Why do I say that? Because if I can afford a gig of cache and it's astronomically more expensive than main memory, what would I be better off doing? Get smaller cache and get more main memory. Instead of a gig of or a gig of cache that I could have bought, I could buy 16 gigs of main memory, go back down to a few meg of cache. Right? Since I'm rolling in money, I might as well get a bigger cache than I'm used to, but not get to the bigger size. In other words, until they equal each other, it's always a good idea to not buy as much cache. That's why you have all these fancy mechanisms, is to make it so that we get the speed of the expensive memory at the cost of the big memory. Okay? Now, there is one twist to that, and one twist to that comes when the next level in the hierarchy, in the memory hierarchy, if it has other attributes besides speed. Okay? And that starts to occur when you get to say something like disk. Okay? When you start getting to disk, or what we usually call secondary storage or tertiary storage, is there's one other aspect to it that doesn't exist in main memory and in cache. What's that? What's very different between disk and main memory besides speed? Volatility. Okay? In other words, when you turn off your computer, information on a disk stays, it's non-volatile, whereas information in your memory, your cache, your registers, all that stuff, wiped out, right? Volatile. So obviously there comes a point where you want to go to disk just for this, the aspect of it that it's non-volatile. No matter how fast, no matter how big your memory is, how fast your memory is, whatever, there's still the attribute of non-volatility that makes disk useful. Right. So, I mean, that's kind of like caching the hard drive for while you're running, right? And then, you write it back when you're done. That's still a form of caching, and it's still a situation where even if you could get your memory as big as the disk, you'd still want that other level. See, when I was talking about the cache memory and the main memory, I said just throw the main memory away because you don't need it anymore, right? Whereas you get to a point where you can't just say, well, main memory is as big as disk, let's throw the disk away. Because there's still that feature, that writing. So that's what you would do, is while you're running, you run in memory, but right before you're, if you're shutting down or whatever, you write it to disk and you get that kind of non-volatility part. But then, when you boot up, the first thing you do is load all that stuff into memory and go from there. Okay? Back when disks were really, really slow and memory started to get cheaper, a lot of people used a trick that made it so you can kind of get better speed for your hard disk. They used to use RAM disks. It's called RAM disk, and they still do it sometimes now. It's when you take a section of memory and basically cut it out of main memory and then load a virtual disk onto it. In other words, anytime you'd actually go to disk, you actually go to this virtual drive instead. So you could access all this stuff on disk, read and write stuff on this disk super fast at the speed of memory. And then when you're about to get done, you actually write it back to disk so that the next time you boot up, it was there. Nowadays, they don't do that much. The reason being is the fact that our caching algorithms and technologies and techniques are so good that you kind of get that performance all the time without having to explicitly say, load up a disk into memory. Okay, but back in the old days, old days where the operating systems weren't as advanced and weren't as efficient, that used to be kind of a way to fake that efficiency. x86, 8086 type of machines, you'd load that much. Like when you start getting to that break before hard drives started becoming, hard drives are fairly fast these days, and our caching techniques are very, very good. Okay. Okay. So those, I mean, that's the main thing I wanted to bring up, just because it was a point that I didn't really emphasize initially going over the introduction and some of the kind of overview concepts. Kind of mentioned it, but not explicitly in that context of the reason we're doing a lot of these things are because we can't afford, to do it the absolute best way. Okay, these are ways to make these things more economical. In other words, studying operating systems in a world where money is no object and everything's, and there's no lack of resources, their operating system class is a lot easier because they don't have to worry about any of this stuff. They just get the best, pop it on there, and done. Okay. And just real quick, we didn't really go into too much detail on we touched on the Windows XP priorities, but I kind of briefly jumped past Linux scheduling. Are there any questions on this? The idea was that they use a somewhat clever idea of kind of giving each process an allowance and letting them pay for time on the processor with that allowance. And then once everybody's kind of used up all their money, right, then they kind of start the week over and give everybody a new allowance. Okay? One thing that does happen kind of when the week changes, okay, is the operating system, the scheduler, kind of looks at the past performance of all these processes and may change how much allowance they get for this next week. In other words, the good processes get more allowance and the bad processes get less allowance, so that in this next go-round there might be a little bit difference in the priorities. And this, by this allowance, these credits, that's kind of a way to do different priorities of these different of these processes. But the whole idea of doing the credit system, right, is to give us a dynamic way to move process priority up and down, so that we can give them differing time slices, right? And the whole idea of doing the kind of everybody spend their allowance this week, and then we'll go to another week, and then everybody gets new allowance, what does that prevent? In other words, how many credits you have that you can spend determine whether or not you're going to get the processor right now. Okay? Why do it in the system of you spend allowance, and then when you get to zero, you have to wait for everybody else to get to zero before you can go on? What does that prevent?
Starvation.
Yeah, that's the term, right? That prevents starvation, right? In other words, if everybody gets a chance to spend their allowance, you'll never get to one of these kind of weeks where somebody doesn't get to actually get on the processor, right? Because no matter how lowly your priority is, no how little allowance you have, you'll at least get to spend it once that week, right? So you'll at least get to run. You might not run very much, right? Everybody else who has these big allowances might run tons of times before you, but every week you'll at least get to spend your allowance and get on the processor. Okay? This is very, very powerful for a system that runs, Linux systems are typically tasked with running many, many processes. They're used in a lot of server implementations, high traffic types of web servers, database servers, stuff like that. Okay?
So why are they all different?
What's that? Well, a lot of it really has to do with what the operating system is kind of targeting. So, Windows XP is probably one of the best operating systems for user response. That's why it's so popular on the desktop, is people have pleasant experiences on the desktop. When everything's running well, the graphical user interface is very responsive. Their foreground applications are very responsive. A lot of people criticize Windows XP for it's kind of wasteful with resources and doesn't handle larger loads in server type settings. They've gotten a lot better than before, but they're still, if you're to look at server type operating systems, Solaris still is, one of the tops. Linux is a very, very strong performer, and a lot of people kind of, you know, the Windows branch of operating systems kind of is seen as the trailer, you know, the person that's trying to catch up as far as those types of things.
But they own
What's
the
that?
PC market.
But yeah, they own the PC market mainly because they pay so much attention to what metric do you think they pay the most attention to? Response time, right? If you target one of these metrics, you can get good response for that at the cost of all the other metrics, right? So why do they have these different systems? Well, because they each kind of have different goals, different markets, right? So if you look at these, you know, the same hardware can run all three of these operating systems, right? You can run Solaris on x86, Windows runs on x86, Linux does. You could have the exact same set of resources and look at them under different loads, under different kind of tasks, and all of them will kind of have, you'll see that they each shine in various areas. Solaris can't be beat when it comes to these very, very big multi-processor machines. Linux just caught up with Solaris, is still catching up with Solaris when it comes to very, very high number of processor, high reliability machines. Solaris can do things in kind of enterprise situations that none of these other guys can touch. You can, like on big Solaris iron, you could pull whole processors out while they're running code and it won't do anything. I mean, as far as like Solaris was still tops in things like telecom and stuff like that. The amount of reliability that they measure Solaris in is off the scale compared to these others. That's usually when you hear, I don't know if any of you have heard the term in enterprise types of situations called 5 nines. 5 nines is a system is up 99.999% of the time. Okay, it translates to like a couple hours of downtime in a year. And you know that kind of, you know, that's a very, very particular set of performance requirements. Windows XP though, as far as sitting there and interacting with it, smoothest, you know, one of the smoothest operating systems you're going to run into. We've seen in their scheduling some of the things that make that happen. These little kind of tweaks to priority based on whether it's accessing disk a lot, whether it's accessing mouse and, you know, graphics and stuff a lot. You'll start getting higher priorities because you're termed as interactive, right? Whereas Linux is about, I have tons and tons of jobs and I want to make sure they all run. I want to make sure that they all get a chance on the operating system. Additional things like real time. Some of the, and we'll see this even more in this next chapter, Linux has capabilities of, we'll see that they can even preempt stuff while it's running kernel stuff. In other words, there's some strict guarantees on when you can say that a process is going to get the operating system again, get the CPU again. Okay, so they all have different goals, and they all kind of have to make sacrifices with their scheduling. Okay, you'll see this type of construct a lot in scheduling. These are the kind of the different queues for different priority levels, and then they just have kind of a queue inside that queue to say all these tasks are at priority 1, all these tasks are at priority 0, and then you just kind of go through and reduce their credits, and as their credits get spent, they move up and down the priorities. Okay, and then, and then once they get to 0, they end up moving over here, right? And then once all the tasks here get over to all the tasks here, then you flip them. This becomes the active array, this becomes the expired array, and then you do the process again. Okay, very efficient data structure, and I mean that's key in these operating system types of, you know, is you want the data structures to be very efficient. They're running many, many, many times a second to get that time slicing going on, so they have to be very, very efficient. Okay? All right. All right, we're going to move on past the, this other example at the end is stuff with Java thread scheduling. We're not going to really look at that. Okay. The reason they have that, you'll see that they do this a lot in this operating system book, is they'll also bring up a lot of topics with Java. One of the main reasons is that Java is like an operating system. Okay, it's an operating system for what? How does Java run? How does Java code run? Do we load Java onto the CPU? In other words, can we take Java code, the instructions, and put it on the CPU? No, we can't. What do we have to do? Translator, a virtual machine, right? So we run the virtual machine on the CPU, and then we take Java code, and it translates through the virtual machine to get onto the machine, right? So Java is like an operating system for the Java virtual machine, right? So that's why a lot of these same concepts come out in Java that we see in operating systems that manage CPUs and disks and stuff like that. Okay? So it's good kind of practice for looking at operating systems. You'll notice that a lot of the things that we might do in operating systems, there's similar calls in Java. For example, threads, running multiple Java processes. What we do in here, these process synchronization semaphores and mutexes and stuff, they come up in Java as well. Okay? So, are there any questions on that kind of CPU scheduling, that low-level task switching? Okay. Yeah.
I just didn't understand the last slide you saw. That's
The queues, those
I
lists.
don't get it.
It's just a data structure that they use to. You can think of each of those numbers, that 0 through 140 or whatever. Those are queues, and each queue is a different priority. Okay, we've already seen that the multi-queue structure. The idea is you put tasks in different queues, and these queues are at different levels, and depending on your level says how often the CPU will service your queue. In other words, get tasks from your queue. The higher the priority, the more often I'm going to look in your queue, and oftentimes the smaller your time slice is going to be. As you go down to lower priorities, I'm not going to service you as often, but when I do service you, you're going to have a longer time slice. Okay? So each of those entries in there was one of the queues, and it has a list of multiple tasks in it. Okay? And then the idea is you go through, once it's all empty, you start over. Go to the expired threads and then make that the active threads.
So for all these scheduling types and algorithms, would you say that the shorter time slices are always get the higher priority, or does it?
Linux actually does it opposite, but I think that's just when it starts getting into real time. For the most part, the best strategy is give the higher priority ones a shorter time slice. The reason being is that the higher priority ones are usually, what do we like to put in the high priority queues? Well, first of all, what are our two kind of major classes of processes? CPU bound and IO bound. CPU bound, they like big bursts of CPU. IO bound likes little bursts. So which ones do we want to put in the higher priority ones? Higher priority queues. IO bound. Okay? We like IO bound in the high priority queues because if we're going to be servicing them often, we like these IO bound processes because they sleep more often. And if they sleep more often, that means they're not going to be hogging the CPU. We're not going to have to preempt them as much because every time we preempt, that's more work for us, right? So the idea is that these higher priority ones are usually going to be IO bound. They're going to sleep a lot. Okay? The ones that are lower priority are usually going to be CPU bound, right? We're going to have to preempt them a lot, right? So the typical strategy is give short time slices to the top because if you sleep a lot, chances are you're going to use a smaller CPU burst, right? If you're given an amount of time and you say you sleep a lot, there's only so many places where you can, you have to sleep somewhere in there, so chances are your bursts are going to be smaller. If I say you hardly ever sleep at all, Well, you're going to have this long stretch, and there's going to be no sleeps in there. So longer time slices. Longer time slices that we don't service as often. Okay? But, and that's the general rule. The general rule is high priority, smaller time slice. We saw that in Solaris, Windows XP. Linux has another class of priorities called real-time. Real-time, again, real-time is not just about servicing things fast. In other words, getting things on the CPU quickly. Real-time, used in the context of operating systems and things, real-time usually means I, as the operating system, when you come to me and say, I want a real-time time slice of the CPU, you can tell me when I'm going to start, like within what period I'm going to start, how long I'm going to have the CPU, and whether or not I won't be interrupted. In other words, you can kind of guarantee me these attributes about how I'll run. Okay, whether it's my CPU time or when I'll get serviced. Okay? But what that also means is that you can fail to give me a time slice. In other words, if you say, I need this much time on the CPU and I need it within this much time, can I necessarily do that? No. Right? If I have a lot of stuff that I need to service, I might not be able to do that. But you can say, no, I can't do that, so then you fail and then you'll have to find some other way to accomplish what you're trying to accomplish. Okay? So that's probably the main reason that those real-time threads have bigger slices, is that they can give better guarantees to real-time. Okay? But you don't want this to be the general rule, because if I say I'm going to give you higher priority, and I'm also going to give you a bigger time slice, what kind of priority do you want? You want that priority, right? That's the best of all worlds. You get your service more often and first, and you have the biggest time slices. So there's usually very strong restrictions on what can be real time in an operating system that supports it. And you're usually root. So like in Unix, only root can run real-time threads. The reason being is you don't want to let regular programmers say they're real-time. Because if they can, there's never a reason not to choose real-time, right? You'll make your text editor real-time just so that you can get the best, right? You'd want to be able to have all your threads real-time and no one else's, because then you'd win. Okay, so given that we have these operating systems with very complex process handling capabilities, multiple processors, right? We have multiple threads, all of these different things, okay? We have a very, very difficult programming problem, okay? And that is the problem of multiple process synchronization, okay? Synchronization is a form of communication between processes, okay? But has some very, very specific requirements that are difficult in the context of multiple processes running. So we're going to look at what is this problem of synchronization, and then some different kind of general solutions, and then these kind of basic primitives, okay? These basic kind of objects that we can use to solve most of these synchronization problems. And then we'll take a look at some of the specific examples. Okay, we're only going to we're not going to get too far into this because it's a hard problem, and I kind of want to introduce most of the problem to you and some of the more general solution so that it can sink in. Because if you're not used to doing multi-threaded programming, semaphores and locking is hard. Okay? Because one of the main reasons it's hard is that it requires a way of thinking in our brain that we don't do normally, and that's thinking in parallel. In other words, the idea of all the combinations of how two things happen simultaneously can happen. Okay? We're stuck in bodies, one brain, one set of eyes, one set of, and we have limited perception that we go along in one thread of execution in our lives, right? So thinking of multiple threads and seeing how they sync up is more difficult than how we're used to solving problems, okay? And our programming kind of follows that. the programming that we usually do up to this point is usually single thread of execution, sequential execution. Okay, that has a lot of luxury compared to multiprocessing. Okay, so concurrent access to shared data may result in data inconsistency. Okay, the problem here is that we have these areas of memory that hold data, hold our values, okay, that we're used to having exclusive access to. We can manipulate it, we can write it, we can read it, and we know that when we leave that piece of data, nothing else is going to happen to it. When you have multiple threads of execution, where the other threads, the other processes can be manipulating that data, we have no guarantees as to what the data will look like when we come back. Okay? Maintaining data consistency requires mechanisms to ensure the orderly execution of cooperating processes. Okay? Our goal is not necessarily, like as an operating system, our goal is not to make sure that our programmers write correct programs. Okay? Our goal is to make it so that programmers get consistent programs. Okay? And what I mean by that is we can guarantee kind of how the order that their instructions will run, right? Or we can tell them the properties of how their instructions run. We cannot tell them that their program is correct. Okay? That's still their problem. Okay? Whether or not their program is correct. But we can tell them that the operating system will run your program in this particular way. That's what we're trying to do. So what we need to do is make sure that we can give them consistency of their data. Okay? Now they can still write bad programs and still screw everything up because they're not synchronized correctly. But we need, as the operating system, we need to make sure that they have the mechanisms to write correct programs. Okay? Consumer-producer problem. Okay? Like one of the kind of fundamental problems of multitasking programs is this idea of producer-consumer. Okay? We saw the general problem of how do we even let a producer and consumer talk to each other. Okay? We saw that with things like a shared memory, right? A shared buffer. We do it with message passing, right? We have these different mechanisms that we saw in the last chapter. That's just kind of where they're going to go for that data. Okay? We still have the problem of how do we coordinate access to that data. Okay? For example, if I say we have a shared piece of memory between process A and process B, and you're welcome to make a buffer there, put produced objects in the buffer, and then the consumer can come and remove produced objects from the buffer. That's fine. Where we get into trouble is managing the state of that buffer and access to that buffer in a way that the programmer will know how that program will run. And that program can run at any speed for either of the processes, and they'll still get consistent behavior. Okay? So let's look at the example. Okay? We've seen code like this before, right? The idea of the producer putting it into this kind of circular buffer, right? And while we have space, right? While it's full, we can't put into the buffer, so we have to wait for it. But then once it's empty, we can put something into it. Okay? So this is the idea of how we put stuff into the buffer. And this right here is the waiting for there to be space in the buffer, because we're the producer. Okay? The consumer, right, has the same idea. If there's nothing in the buffer, I do nothing, I wait. But once something's in the buffer, I can consume it, and I have to kind of update the count so that it knows that I've consumed something. Okay? Now, look at mainly these areas right here. Count. What does this do?
The producer, whatever
No, what is this? Just the statement. It's a short answer. Increment count, right? In other words, take what's in count, add 1 to it. Okay? Why is that important? Well, this idea, right? While it's the buffer size, in other words, it's full, I have to wait. So by incrementing, I could get to the point where I need to wait. In fact, that's, if I'm producing very quickly, that's what's going to happen, right? Is we keep producing, and then we get to the point where this is the last one we can fit. Increment, now we're full. Okay? All the while, what's happening on the other side? Decrement, right? This consumer is going through and trying to reduce the count. The producer is going through trying to increase the count. Well, in perfect balance, we're always producing and we're always consuming and everything works fine. Now, if this count was ever different, depending on whether you were viewing it from the producer or consumer side, bad things can happen, right? What if the producer sees the count as 1 less than it actually is? What could happen? In other words, the buffer size is 4. Okay? And let's say there are 4 unconsumed objects in there. But let's say we see the count as 3. What will happen? And it will put 1 more, right? It'll overwrite one of the entries in our buffer. So what happens to that entry? Gone, right? So that's bad, right? What if the consumer, right, sees the count as 1 higher than it actually is? Let's say it sees it as 1, but the count's actually 0. What will it end up doing? Right, it'll read it, right? It'll go and say, there's an item. I'm going to go get the item, and it turns out that item's garbage. Okay? So, both sides having the same view of that count variable is critical. Okay? Normally not a problem, right? Because really, only one of these statements can be executed at a time. Let's say we're on a uniprocessor system and we're just time slicing. Right? Only one of these count plus plus or count minus minus can be executed, right? Because if one's suspended, it can't be running count plus plus, so this other consumer can run count minus minus, right? Okay? And that would be fine if this is the level at which we did context switches. Okay? In other words, if these instructions were the level at which we switch from one task to another. What language is this? C. Does C run on a processor? Do we have any processors that read C and execute the statements? No. What do our processors run? Assembly, machine language, right? So, how do we run this? Compile it into machine language, and then run the machine language on the processor. Is this necessarily one machine language instruction? It's not, right? So, this turns into, right, a set of machine instructions. Okay? So let's look at these 2 sections. This is the same counter plus plus, right? This statement turns into this, right? This statement turns into this, okay? So now it's gotten a little more complicated. Now instead of just time slicing between count plus plus, count minus minus, right? We're now time slicing between 3 different instructions on each side, okay? What do you notice about this particular interleaving, this particular mesh of those 6 instructions? Okay, let's walk through it. Well, let's go through the individual ones, okay? Register 1 equals count. So our CPUs don't work directly on information in memory, right? Typically we'll load something from memory into a register and then operate on the registers. So this is saying register 1 Load the memory space where count is, the variable count. Then what do? We say register 1 equals register 1 plus 1. So we increment register 1. And then what do? We store it back in the variable count. So this one statement does all three of these. Same here, except we are subtracting. It could be the same register. Why does it matter whether or not it's the same register? Because if these are in two different processes, right, we're only running one at a time. If we were to switch to another process, is that the same register 1 as this process saw? Physically, yes, but logically, no. Because what will happen when you switch? Context switch happens, right? So in other words, the value in register 1 here will be saved, and the value that this one expects there will be loaded. Okay? They're making it two different registers because that is easier to see, right? If they're in two different registers, there's no question that they're two different values. Okay? But just remember that back in the back of your mind that this could be the same register, but they're still actually different in the terms of a context switch. Okay? So, producer executes register 1 equals count. So we've loaded the value of count into register 1. Then register 1 equals register 1 plus 1. So we increment it. Okay, here's our problem now. What happens in this next statement? In S2. What is the value? Oh, here, sorry. The initial value of count is 5. Okay, so we load 5, add 1 to 5. So what do you notice here? Right. Why hasn't it been saved? Because we haven't gotten to this statement yet, right? And you're right. We've context switched to another set of instructions before we got to that statement. So what happens here? We load the original value of count. Okay? Then we decrement it. So now, notice we have two different views of the count variable, 6 and 4. We save the value of register 1, in other words, from the producer thread. What does it write? 6. But right after that, we're writing over that same value with 4. Okay? What ended up happening is we've executed count plus plus and count minus minus simultaneously. Okay? Simultaneously enough because it expanded into 3 different instructions. Okay? In other words, it expanding into more instructions made it so that we can kind of do half of one instruction, do a little bit of the other instruction, and then finish the first instruction. Okay? So what ends up happening is we have 2 different views of it, and what's very, very bad about this, okay, the worst part about this, is that these context switches here are somewhat arbitrary. Right? We've already seen that what time slice you get can change all over the place depending on the scheduling algorithm, right? You could get more length on one of these threads than on the other, who knows? So what do you notice that if I run these two programs, right, the producer and consumer, if I run them and we go like this, what's the value of count? 4. Okay? What if the consumer gets a slightly longer time slice? What is now the value of count? And why? The consumer. If the consumer gets a longer time slice, what is now the value of count? So you're saying 6. Why is it 6?
Basically the last 2 switches will be flipped,
right? Right, because we'll continue running the consumer, and then task switch, right, context switch back to the producer. So now the producer store command is after. So now the value is 6. So these two programs will have two different results just based on how long the time slices are. Why is that bad? Because it's not deterministic from the programmer's standpoint. Okay? Programmers, as a rule, should not like things that are non-deterministic. Right? Things should happen in a particular way every time you run.
I didn't understand that the last part, if the consumer part have a longer time slice, then the producer part, how the producer part come back, or the count comes 6.
Well, because we're going to end up having to run both threads, right? What does a longer time slice mean? It means that we won't task switch until later, right? So if the consumer has a longer time slice, it gets to execute more instructions before it's interrupted. Well, if it can execute all 3 of its instructions before it's interrupted and it goes back to the producer, these will be switched. The only reason this one is here is because it was interrupted here and went to the other process.
So in that case, what can be the count if it's run longer? It's going to be probably even smaller than the count. Right?
No, well, we only know that these 6 instructions are running. We have no idea what happens outside of this. Well, all I'm saying is a slightly longer time slice that allows one more instruction to run will change the value. Okay? What would make these 2 programs behave correctly?
They were each allowed to finish their instructions.
So in other words, all 3 of these instructions run, then all 3 of these instructions run. Okay? It's even more detailed than that. As long as this storing of this value happens before this loading of the value, it works how we expect. Right? Because if we're always loading a value that's completely done being worked with, we'll get a consistent view. Right? In other words, this one can increment it and this other one can decrement it. The problem here is that we're incrementing or decrementing a stale value. Okay? This is process synchronization. A lot of it is centered around solving problems like this. Having a mechanism for saying, look, I need to make sure that these instructions happen together. Because if they don't, I'm going to get inconsistent values. Okay? The term that will come up a lot with this is atomicity. Okay? It'll come up later. Atom. Oh, right. Okay? Atomicity. Okay? Atom. Right? Atom, for the most part, is, until quantum and stuff like that came along, is we think of atoms as the smallest unit that something can be broken down into. Okay? So the idea here is that if this, right, a single instruction can be performed atomically, in other words, once I start it, it completes to the end with no interruption, no breaks, right? That's good. Because if we can guarantee atomicity, right, then we can say these things will run in a consistent fashion, okay? That's not to say that if you're running process 0, right, the producer, let's say, and the consumer, okay? This idea of running these as a unit, as a single unit, doesn't guarantee that, right, that's counter plus plus, this is counter minus minus, okay? This, this atomicity doesn't guarantee which of these will run first, okay? Because this can still run, let's say faster than this runs, okay? Or vice versa, or this could run faster and that's slower. We still aren't guaranteeing which of these statements runs first. We're just guaranteeing that the whole statement runs before the other statement. Okay, everybody clear on that?
How does it know?
That's what we need to solve.
Okay.
Is how do we make it so that it runs like this?
I mean, when you say something's atomic, it could be the whole program,
Sure.
right?
You could guarantee atomicity for the whole program.
Okay.
You'll be slow.
Yeah.
Right? But there's there's tons of problems surrounding this, and all of them kind of, they use different techniques for, and that's what we're going to explore. Okay. But
Now, would that have anything to do with the idea of, I remember in assembly we had to put no operation lines in there because of the...
no ops can fake some of this if you're doing no ops are just basically waiting, or just wasting cycles. Now that might be for that might synchronize some things in a sequential program, but this is a lot more formal than just waiting. So no ops can take time and stuff, but this is...
I guess what I'm asking is, like if you change the value of count on one line, and then it's accessed on the next line by another process, can it go straight from one to the other without...
As long as the order is guaranteed. I mean, in other words, as long as the parts that change it are guaranteed to complete. There's actually synchronization places where reading is easier than writing, mainly because both of you reading a value, even if it's stale, it doesn't matter. It's just kind of like you read it before the change statement.
Right.
So it's actually easier. So it really depends. But typically, once that atomicity is satisfied, you should be able to switch however you want. In other words, as long as you're outside these sections, you should be able to directly go to whatever other instruction you want. Okay? This is going to be known as a critical section. Okay? And critical section is very important in multi-threaded programming. A critical section means within this, you have to perform this in a particular, no one else can manipulate these variables when I'm in this critical section. Outside of it, I don't care. But everything between the start and end of a critical section needs to happen kind of as a unit. You're welcome to do other stuff in another process. You just can't get into these variables. Okay? Critical section has 3 different requirements for this is the critical section problem, this idea that there's a section that must be executed in a particular way. That's the critical section. So that's the problem is, how do I make sure that it's executed in a particular way? In order to satisfactorily solve this problem, there's 3 attributes. Mutual exclusion. Okay? Mutual exclusion means that only one of these processes can be manipulating the variables within the critical section. Okay? Critical section, critical section. Mutual exclusion says only one of these can be manipulating counter at a time. Okay? They're both welcome to access counter and manipulate it. They just have to make sure that the other one is not manipulating at the same time. In other words, you either have to bump down or you have to bump up. You cannot do it at the same time. Okay? And if you want, you can say this has to be atomic. Okay? So, mutual exclusion. These two are harder. Mutual exclusion is easy to kind of comprehend. One, not the other, right? These are harder. These are to guarantee that both of the processes get to execute their instructions. Okay? Progress. If no process is executing in its critical section and there exist some processes that wish to enter their critical section, then the selection of the process that will enter the critical section next cannot be postponed indefinitely. Okay? So, what that's saying is that if I get to manipulating counter, okay? Obviously, if one of them is manipulating counter, the other one can't because of mutual exclusion, right? If you get there and you want to execute counter, you want to manipulate counter, and somebody else is already manipulating counter, you can't because of point 1, right? But there's also the idea that if you get to counter, and nobody's manipulating it, and you go through some mechanism to say, hey, I'm going to manipulate counter, you may or may not have to wait. Okay? But if you do have to wait, okay, if you do wait to manipulate counter, you can't do that, you won't be made to wait indefinitely. In other words, there will eventually come a time where you can progress. Okay? That seems like it's real easy. You just let them go, but we'll see that as it gets more complicated, you could get to the point where you're always waiting. So you need to be able to make progress. Okay? Bounded waiting. A bound must exist on the number of times that other processes are allowed to enter their critical sections, after a process made a request to enter its critical section, and before that request is granted. Okay? This one is saying that if I have multiple processes, right, wanting to access this critical section, okay, it's just saying that if I have to wait, all right, and everybody else gets to go through their critical section, you'll eventually come back to me. In other words, we won't get in a situation where all of them get to keep executing critical sections and I have to sit there and wait. In other words, there will come a time where it gets to be my turn because they've already executed their critical section. Typically, just to make it easier, is if two processes get to a critical section, right, and one of them wins, one of them gets to execute their critical section, they won't get to execute it again until I get to go. Okay? It might not be that simple, but that's the general idea, is that you can kind of give them a bounds of how long they'll have to wait. It's not just time, it's really turns, right? There's a bound on the number of turns that everybody gets. Okay? And the reason we can't talk in terms of time is because all this weird time slicing is going on and all that stuff. So you have to kind of talk in terms of turns. But these three different things, if we can solve those, we make it so that we can do these critical sections in multiple processes, and they can, and we kind of let everybody know that if you run these parallel processes and they access these critical variables and resources, that you'll be able to get through the program. Okay? That's not to say that programmers can't screw this up and make scenarios where where things end up locking up or everybody's waiting, but it's not because of the mechanisms we gave them. Okay? So I didn't take a break, but I'm just going to go through Peterson's solution and then we'll quit for today. Okay? Because this is kind of a very simple, high-level solution to the problem, so that you guys can kind of go back, think more about this idea simultaneous access to variables, look at the solution and how it solves it, and really absorb it. Because you're really probably going to have to sit here and look through the code and walk through the code to really click with how this solves our synchronization problem and satisfies those conditions. Okay? So, the idea here, okay, is that we share two variables, okay, and these are outside of the variable that we want to manipulate. In other words, these variables are just to support what we're going to call locking, okay, because locking is, and when I say locking, I'm saying lock a section so that one can run, and then you unlock, and then the other one can lock it and run, okay? So this is just to support that mechanism, these variables, okay? Turn, okay, represent whose turn it is to enter the critical section, okay? So the processes kind of get numbered, okay? 0 process, 1 process. If turn equals 0, it's process 0's turn. If turn equals 1, it's process 1's turn, okay? That's not enough. You can't just have turn. You have to have another set of variables here, this Boolean flag, okay? And this says whether a process is ready to enter the critical section, okay? And the two flags are one flag for process 0 and one flag for process 1, okay? So each of process of flag 0 and flag 1 can either be true or false, okay? The variable turn indicate whose turn it is. Flag array, right? True implies that the corresponding process is ready to enter the critical section. Just like I said before, 0 for 0, 1 for 1. If it's true, it means you're ready to enter. Okay, so we have these, right? We can initialize turn to either process, and then flag should be false, because we haven't gotten to the critical section yet. So, what do? Well, first, when we arrive at our section where this piece of code, okay, this piece of code will show up around our instructions that we want to lock, okay? So this critical section, you can think of that as like counter plus plus or counter minus minus, right? Those different things that we saw in those two processes, okay? So, as we're approaching that critical section, right, if we get to the top of this, we know, well, I'm about to run. I'm about to run my critical section, okay? Flag I set to true. I is me, okay? So when I say process 0, flag 0 equals true, I'm indicating I am ready to run critical section, okay? Who knows what flag 1 is saying? I don't know yet. I haven't checked. Turn equals J. That's saying I'll let the other person, it be their turn. That might seem weird. Okay? And then we get to this while loop. Notice this is an empty while loop. An empty while loop is wait. Right? Because you'll just loop doing nothing while the condition is true. Okay? While flag J and turn equals J. Loop. Okay? What that's saying is, while the other person is ready to run critical section, and it's their turn, I will wait. Right? Okay? That seems kind of weird. In other words, we're about to enter this critical section, and we get all ready. We say, I'm ready to run my critical section, and I want to run my critical section. And then we get to this point and say, but if you're ready, I'll let you go. Right? Okay? So then we sit there until one of those conditions becomes false. Right? Because you loop while something's true. If it becomes false, you finish the loop. In other words, we can proceed past. Okay? let's just say that that works, okay? Let's pretend we know somebody will get to run their critical section. Let's just assume this thing works. And somebody gets to run their critical section. They run it, and they get down here, and what do they say? I'm done running my critical section. I'll set my flag to false because I'm not ready to run anymore. I already ran it. And then I'll run some other code until I get back and loop and do it again. But what I'm saying here is I'm done with the critical section. This is kind of saying it's all yours. Okay? So, let's say I'm process I, and process J is ready to run its critical section, right? I get to here and I say flag J is ready, is true. And I just set turn to J, and turn J is true. That means it's the other process's turn, okay? This is true, so that means process J can run. So now let's switch views to be process J. Now I'm process J over here, okay? So when I get to this, flag J is true, but what does turn equal? It actually equals me, right? But in this case, I'm I, and the other one's J. In other words, this equals 1. Let me back up. I'm going to write what the values are of things up here. Okay. Flag 0. Flag 1. Turn. Okay, we'll start off. Turn equals 0. False. False. Okay? Now, whoever's running is I. Whoever's not running is J. Okay? I am process 0. Okay? So, I get to the first line. Process, what is I in this case? I is 0. J is 1. So, when I get to the first statement, what will I do? Set flag 0 to true. Turn equals what? The other guy. So that is 1. Okay. In this case, I get to while flag J and turn equals J. What is flag J? What's J? 1. What does flag 1 equal? False. False. So what do? I don't do the while loop. I keep running. And I run my critical section. No problem, right? I hit here, and I say flag I equals false. Change that to false. I loop. Okay? No problems there, right? That was just process 0 running through the whole thing. Now, process 1 over here running through the whole thing. What's I now? I is 1, J is 0. Now, since I'm on this side. Flag 1 equals true. Turn equals 0. While loop, flag 0, false. I can skip it, run through critical section, Flag 1 becomes false. Done. So running through either one, no problem, right? We can go and run our critical section, run the rest of our code. Now, where do we know that this stuff gets tricky? When we're switching, right? When we're switching back and forth. So, let's run line 1 as process 0. Flag I equals true. So that means flag 0 becomes true, right? Let's say it gets to run the next statement as well. So turn equals J. What does turn now equal? 1. Interrupt. Context switch. I'm now process 1. Flag 1 equals true. I'm about to set turn equals J. Context switch. Right? I'm at while, right? While flag J, true, and turn equals J, true. Both true. What do? I wait, I wait, I wait, I wait until something changes. What will change? Context switch. Process 1 again. Now what statement will I execute? Turn equals J. So turn now equals what? 0. I get to while. Flag J. Flag 0. Is it true?
Yeah.
Turn equals 0. What will I do? I will wait. I will wait. Right? What will happen? Context switch. I'm now process 0. Flag 1, is it true? Yes. Turn equals 1? No. False. What will happen? I continue. Run my critical section. I'm in the middle of my critical section. Context switch. Flag 0, is it true? Turn equals 0. True? True. So what do? Keep waiting. Wait, wait, wait. What will happen? Context switch. I'm process 0 again. Continue my critical section. Get to here. What will I do? Flag 0 equals false. Boom. Context switch. Flag 0 equals true. No, false. I can now continue my critical section. Okay? What did you notice about that?
Never were able to access critical sections at the same time.
Everything between these, only one could run. Okay? The other thing is that by making it a wait loop here, we ensured that only one was waiting at a time. We also made sure that by the time you get down here, the other process would get to run after only one go-round of waiting. We've satisfied our different properties that we saw, those 3 properties. Okay? We satisfied mutual exclusion. Only one could run the critical section. We satisfied progress, right? When no one was running, somebody's going to go forward. Okay? And we satisfied bound wait time by saying that Only one go through is all it takes for the other system to, the other process to get a go. Okay? This type of idea is the basis for all the other synchronization we're going to look at. And you see now why I'm saying it's hard? This is a hard chapter because it takes running two different things at once. Sometimes one's running fast, sometimes the other one's running fast. And we need to say, you need to really carefully say what, them both trying to manipulate the same variables, okay? The thing I want you to think about, okay, for Thursday, and the thing that we're going to discuss first thing Thursday is, why does the phenomena of this manipulating counter at the same time, right, where we could get two different views of the variable, how does this solve that? In other words, can we still have a situation where they can both kind of change the counter? How is the problem solved with this mechanism? In other words, walk through, get those counter changes as close as you can together, right? And see why you still don't have a problem. Okay? Because once we see that, we'll see that we've made it. What happens is, if we can make sure that that problem is solved, we can actually grow this out into being able to manipulate counter. In other words, just put counter in the critical section, and we've kind of made it so that we can do more powerful things just with this mechanism. All right, that's it for today.
So, realistically, how many machine level instructions are actually using a time slice?
Oh, I don't know. I don't know what the scale is really. I mean, honestly.
Like hundreds or 10? Or more
Well, okay.